Are you guys actually making use of the videos?
Yeah.
So let's just wait a minute or two more.
You get on the way.
Alright. I'm having trouble with this pointer. I don't know if it just doesn't seem to want to go back and forth, and I just changed it. Does anybody know maybe how to activate this guy? No, it's on, but you see I can't point. No, I mean the USB stick.
The other set, there's another
Oh well.
Oh, it just appeared for a bit.
Sorry?
There was just an arrow for a bit over there, going diagonally across
It
the
doesn't matter. Alright.
There.
Yeah, that's my Alright everyone, so welcome. Today we have quite a hectic program. We're going to do today alkene metathesis in detail, alkyne metathesis, and so that's what we're going to start today's lecture off with. Basically, what is alkene metathesis? The way this is sort of in a nutshell what it is. If you take two alkenes, right, decorated with different substituents, here you see R1, R1, R2, R2, and you perform alkene metathesis catalytically, you end up with two new alkenes where each alkene is decorated now, or at least has the substituents R1, R2. So what has actually happened here? A very nice analogy of this is if you imagine being on a dance floor, and this is one dance couple and this is another dance couple, and if they stand next to each other, right, and then they swap partners, you end up with new alkenes. So that's basically what alkene metathesis is changing of dance partners. Right, you can see that's very nice. That's one dancing couple, that's another, they come together and then they swap out. That's alkene metathesis in a nutshell. Now we get different types of alkene metathesis, lots of different types, but they're all variations on the theme, right? It's the switching out of dance partners. And well, this is the example we just had at the top here is an example, and I'll show it again here, of so-called cross metathesis, where essentially, as you can see here, we have a process like we have there where they swap out via metathesis and you generate a new alkene that has these different groups. You in fact generate two products here. We'll look at that in a minute. If you take two alkenes and you perform metathesis, you always end up with two products, two new alkenes, right? All right. So that's cross metathesis. We're going to look at the mechanistic details in a moment. We then have the next variation on the theme is so-called ring closing metathesis, where you start off with a diene, this is a diene, and basically perform metathesis, you get closure of the ring and you generate ethylene, right? The mechanistic details we'll look at momentarily. You have ring opening metathesis called ROM, where you start off with a cyclic alkene with another alkene, perform metathesis on that and you get a new product. You have so-called ring opening metathesis polymerization, ROM, where you start off with alkene monomers and you catalytically polymerize it using so-called ring opening metathesis polymerization. This is an example of ring opening metathesis polymerization. This is an industrial process. Here we have cyclooctene, right? And if we, this is the catalyst that is used to do ring opening metathesis polymerization and forms this polymer. And that is in fact used industrially, and it's a very useful starting material. We have also acyclic diene metathesis polymerization. So here in this variation, you start off with a diene, an acyclic diene, and you polymerize it using metathesis. So those are the variations on the theme. We have, let's just go through them again. Simple cross metathesis, ring closing metathesis, RCM. This is very often employed in organic synthesis. We'll look at some examples in a moment. Ring opening metathesis polymerization. This is an example of that. And admit, which is acyclic diene metathesis polymerization, you see over there. Now, this is a very important process, and it resulted in the 2005 Nobel Prize being won by these three guys, Schrock, Grubbs, Chauvin, and I think I mentioned in my previous course, this guy actually doesn't have a PhD degree. At the time that he won the Nobel Prize, he only had a master's degree, right? Which is quite interesting. I think he's in the meantime obviously been awarded several honorary doctorates, but he doesn't have a formal doctoral degree in chemistry. Now, the reason why they won the Nobel Prize and shared it is because, of course, alkene metathesis, it turns out, is something that is heavily used in organic synthesis, which we will see later in the lecture. I want us later on to sort of look at some applications of alkene metathesis in organic synthesis, but also you saw with that example of the ring opening metathesis polymerization of cyclooctene, also used industrially to make a variety of very valuable commodities, right, starting from alkene. So very important process, and I would say these guys are the ones that pioneered the whole thing. Now, as I said, the way to think about it is change your partner with dancing. That's not really my own idea. I sort of stole that from the Nobel Prize website, and actually this comes from their website, 2005nobelprize.com, which I think very nicely shows via analogy what metathesis is all about. So let's have a look at that. Let's start again. All right, so check it out. So that's an alkene. That's what's happening in metathesis.
That's cute.
Very cute, huh? And so these are different alkenes, and then they come together, and then they swap. Now that process of swapping out partners is actually catalytic. So this process requires a catalyst to facilitate that. So it's not like really on a dance floor where you just grab another dance partner. You need a catalyst to do it. Okay, so that's basically what metathesis is all about, alkene metathesis. And I would like to just say, this also comes from the nobelprize.com website. This is taken from Chauvin's lecture. 1964 was sort of a very important year. They discovered that if you take propylene and at pretty high temperatures react it with molybdenum or tungsten hexacarbonyl and alumina, so sort of a heterogeneous process, you get some sort of an alkene metathesis process, as you can see there. You can sort of see that that's being chopped up. Well, you sort of have a metathesis of propylene going on there, self-metathesis. And also, in the same year, Nutter, who's we heard about last week, is the guy that's famous for polymerization. He found that you can actually, depending on which catalyst mixture you use, you can polymerize cyclopentene using tungsten hexachloride or molybdenum hexachloride, and you get basically different products. So the only way that this can proceed is via some sort of a metathesis route. The metathesis, another way of thinking it is, if you have an alkene taking a pair of scissors and cutting it in two, right? If you're opening up a ring, or if it's acyclic, bringing them together, pinching them together. 1964 was also an important year because Fischer made the first example of a so-called tungsten carbene. We've all heard about this, yes?
Is aluminum oxide a co-catalyst, or is it like a complex there?
That is not really a co-catalyst, that's sort of the surface. So this was a heterogeneous process. Okay, so these are sort of actually heterogeneous processes here. Now this is a very important discovery, Fisher, 1964, we all know about this. And the first example of a metal-carbon double bond, which will become important later on, because you will see that these metal-carbon double bond alkenes are heavily implicated in alkene metathesis. So when they first discovered this, they were interested in trying to understand the mechanism, right? If you take two alkenes, R1 and R2, and you combine them, so let's write that down. If you do some sort of a cross metathesis, what they get is R1, R2. So the question was, what is the mechanism? And this is, of course, catalytic. What could possibly be the mechanism to arrive at this thing over here? And basically, they had a couple of ideas. The first idea...
Writing a really important email to a colleague.
The first idea, what's this? The first idea was that the two alkenes interact with N, which is some sort of a catalytic center, and form a sort of a cyclobutane or a cyclobutadiene intermediate. Something like this, and then that sort of rearranges and decouples from the metal and you form the product. Right? You see, this is a cross metathesis, basically what I've represented there. That was an idea, a reasonable mechanistic explanation for how we get from there to there. The next idea, so people were just sort of thinking of ideas, right? Well, you could explain it in this way, that it goes via an intermediate that looks like this, where basically the alkenes essentially break the double bonds and form sigma bonds to the metal. Right? And you form a sort of a tetramethylene complex. Now the problem with that, of course, is that it would elevate the oxidation state of the metal by +4, right? So that seems a little bit unreasonable to me. Moreover, what else is unreasonable about this structure? Yes, it's highly strained. So that would be, I would say, pretty unlikely. But anyway, it was on the table. And the next idea, this was actually proposed by Grubbs at Caltech, was that it goes via a metallocyclic intermediate, which then undergoes some sort of a reductive cleavage to form the product. So those were the ideas on the table. People didn't really know what the mechanism was. Now, here we have a couple of examples of active alkene metathesis catalysts, the ones that were sort of the first, well, certainly this was the first reported example by Schrock. So Schrock made this tungsten complex, and it's in a pretty high oxidation state, and he found that this tungsten compound actually does metathesis with 2-pentene, right? That's the first isolated example, sometime in the 1970s, right? And these examples here, I just put them on. These are sort of more recent examples of active alkene metathesis catalysts from Schrock, right? And basically what he did later on is he decorated this with these imido groups. So we've sort of encountered something similar in our discussions of the synthesis of ammonia. But basically he found out that these guys are pretty active alkene metathesis catalysts. And you can see he decorated it with a CF3 group, and that sort of increases the activity of the metathesis catalyst. What we see at the bottom here is actually what happens if you react this. So this is an alkylidene complex, right? It's a Schrock carbene with trimethylsilyl ethylene. And you can actually see the formation of this four-membered ring system, which is an intermediate in the alkene metathesis. We'll look at the mechanism in detail in a moment, but you'll see that something like this is an intermediate one requires. They observed it in situ. spectroscopically. Now, this guy here is, as I said, what sort of a complex? It's an alkylidene. Now, what would you say is the oxidation state of the tungsten? +6, exactly. It's Schrock type, that's 2 minus, 3 minus, 4 minus, 5, 6. So Schrock alkylidines tend to have the maximum oxidation state, they tend to, right? Remember that whole discussion we had also in the 2000 course, whether something is Fischer or Schrock type really, you know, it depends. But that's definitely Schrock type, Schrock type, Schrock type. Anyway, so that I just want to mention that Schrock was, I just put this slide up because I want to just, for the sake of historical accuracy, prove to you that Schrock was very much involved in this work. I'm not going to talk so much about his developments in alkene metathesis, but he really was, in a way, the first. What I'm going to spend my time on actually is talking about ruthenium-based catalysts which come from grubs. Right, and I talk about these because these are the ones that are really used quite often in organic synthesis and so on. So in 1995, Grubbs makes this complex over here. And he does this by a very elegant, so if we just concentrate on the top here, by an elegant dinitrogen elimination route. Now, so what he's basically doing here is he starts off with this ruthenium-2 complex, so ruthenium dichloride tris cyclohexylphosphine. So R in this case is, let me just write that down, is tricyclohexylphosphine, so it looks like, it looks like this. So, and, well, this is one way that you can make a carbene, actually, is by, what happens is nitrogen is eliminated, it's entropically driven. That uncovers basically a carbene, a free carbene, PHCH, with the lone pair sitting on the carbon, which then attacks the ruthenium, you get the carbene. Now, he showed that this compound is active in alkene metathesis, right? What I showed on here, actually, is basically well, just the reaction conditions that they employed to make this complex. They did it at -78 because these are so-called diazo compounds. Diazo compounds tend to be very reactive, right? And in fact, some of them are even explosive. So you've got to work very carefully with them. I know a guy in Bonn that was making some of these and he had to wear like metal gloves and stuff. It was all quite scary. But anyway, that's a very useful synthon to make carbenes. That's how I made it. And then basically what you see here is he just basically, you add the diazo compound to the ruthenium and then you stir it at room temperature and you can isolate the compound. And he showed that this compound does ring closing metathesis of this guy here. So if you take this, add this catalytically, it closes up the alkene. So this is a type of a ring-closing metathesis reaction and you liberate ethylene. So that was the first example of from Grubbs. So Schrock has made some examples, right, based on tungsten, and now old Grubbs comes along and makes these nice complexes. That is the X-ray structure of this guy, or at least a space-filling model. You can see you have some sort of a, let's say, distorted trigonal bipyramidal geometry around the ruthenium center. Now we're going to look in detail how this guy actually does this catalysis. All right, so very often people call this guy here Grubbs' first generation, the first generation Grubbs catalyst. All right. Now the great thing about this is we've got a phosphine here. Right? So we could replace this phosphine with another ligand, couldn't we? And that would also potentially be an alkene metathesis catalyst. But before we get to that, let's review the mechanism. For those that haven't done it, and for the sake of refreshment, let's look at the mechanism. This is the mechanism of sort of the general mechanism of alkene metathesis, I represent M double bond here. This represents the carbene functionality of the ruthenium, or if you're using, this is a general mechanism. You can also use it for Schrock complexes. But what happens? Let's look carefully at this mechanism and make sure that we all understand it. You have an M double bond C, right? It sees the alkene. What happens? It forms a metallocyclobutane ring. How does that happen? It happens by something called a 2+2 cycloaddition reaction. So what you can imagine happening is you have something like this. Let's just say Cr2. It sees the alkene. Let's just leave the substituents. And this is what happens. That's how one forms this intermediate metallocyclobutane ring. Okay. And what then happens is, what happens next? You then have this unstable four-membered ring system, and to alleviate ring strain, it does another 2+2, well, it's not really a 2+2 cycloaddition, it's now called, as we see in the next step, a cycloreversion reaction, and basically the ring opens up, right? The ring opens up, and let's see what happens mechanistically down here. It does something like this. So you form the ring, you've got the electrons in there, and then the bonds break, and you end up with an alkene product, as I've written it down here, it wouldn't be that, plus a new carbene. Does everyone see that? You guys follow? So we get a 2+2 cycloaddition of the alkene to the carbene compound, formation of a pretty reactive or unstable four-membered strained ring system, which undergoes a cycloreversion reaction. The electrons are pushed around and we form that guy there. That's what's happening in terms of electron pushing, and that's what's represented in this mechanism here. This is the mechanism of Chauveau. He was the one that correctly sort of elucidated the mechanism. Remember in the beginning I showed all those weird possible mechanisms that scientists were using? This is the correct mechanism, which was later elucidated by lots of experiments. So here you have the 2+2 cycloaddition, you here have the cycloreversion, and then another alkene comes in and it coordinates to the new carbene that has been generated. You get another 2+2 cycloaddition, and then you form the product. So this is an example now of how you would do cross-metathesis of this alkene and this alkene. So you have a catalyst, you have two alkenes, one decorated with an R1, one decorated with an R2. You do the alkene metathesis in this way. The first alkene coordinates, you eliminate ethylene, and you form this new carbene. The second guy comes in, the R2, you get a 2+2 cycloaddition, cycloreversion, elimination of the products, and you reform. Do you notice in this step here with the cycloreversion, you again regenerate the catalytically active carbene. So that's the mechanism of cross-metathesis, according to Chauveau. Yes?
Can you investigate the metallocyclobutane in situ as well? Is that how they figure it out? Or?
That's a good question. That's a good question. I think yes. If you decorate it with the right substituents, I'm speaking under correction, and you could potentially stabilize it and at least observe it spectroscopically.
What does the loopy like mean?
Oh, that just means that
It's cis or trans?
it's cis or trans, exactly, precisely. Now we're not going to go into those details today because there's a whole field devoted to driving the stereoselectivity cis and trans. I think that's way beyond the scope of this. I just want everyone to really understand this mechanism. So this is the mechanism for cross-metathesis. Now remember, I said there's variations on the theme. We have cross-metathesis, we have ring closing metathesis, ring opening metathesis, all those things. the mechanisms are always basically the same. It's always, you start with the carbene, which is the active catalyst. You have a 2+2 cycloaddition. You have a cycloreversion followed by another alkene coordination, another 2+2 cycloaddition, another cycloreversion, and then you eliminate the product. Let's look at the mechanism of ring closing metathesis. You will see it's basically the same. Here we start off with the carbene. I just represented MCH2, right? This would, for example, be, Grove's catalyst, for example. But that's basically the active species is the carbene. Now check out what happens in this variation on the theme. Basically the same thing. We have the diene, it coordinates. Check it out. Sorry, not the carbene, the alkene. One of the CC double bonds sees the metal carbon double bond of the catalyst, and basically they see each other and they form an association. That's the first step. Then you have a 2+2 cycloaddition reaction, okay? And again, like we had here, you form this four-membered ring system, right? That four-membered ring system is an intermediate. It's pretty reactive. And it undergoes now again a so-called cycloreversion reaction. Check out how the arrows are moving. So check it out. You form a metal carbon double bond, a new metal carbon double bond with this guy here basically tethered onto the metal, and you eliminate ethylene. Do you all see that? So you have, in summary, alkene coordination to the carbene, 2+2 cycloaddition, formation of the metallocyclobutane intermediate, cycloreversion, as we saw before, it's all the same, elimination of ethylene, and now we have this new system here. But now, because I have an extra alkene in the backbone of this, this is an alpha omega diene, isn't it? What can happen now? Well, what can happen is, because we have another double bond that's actually linked there, is we now have an intramolecular 2+2 cycloaddition, formation of the ring system, cycloreversion, and check it out, we form the alkene plus ethylene. So does everyone understand this mechanism? Anyone? Any questions? Sure. We get alkene coordination, 2+2 cycloaddition, cycloreversion. Then we have basically a metal carbene. It sees the olefin functionality at the end of this chain, which is now bound to the metal, right? Do you see that? That undergoes a 2+2 cycloaddition and forms this system over here. And that then undergoes a cycloreversion reaction. Look at how the arrows are being moved. So that metal carbon bond breaks to form a double bond there, which is what we see in the product, plus an M double bond C pointing down. And then the whole process starts again. But you see, the mechanism is the same. It's just we've used an alpha omega alkene, but the mechanism is the same as with cross metathesis. It's exactly the same. And this is the mechanism of ring opening metathesis polymerization. Again, it's the same. What we have here is we start in this case with a closed ring, all right? And depending on the conditions, we have again 2+2 cycloaddition. It's also called a retro 2+2. I call it a cycloreversion reaction, or 2+2 cycloreversion. Some people call it a retro 2+2. And what happens? Well, if we have a retro 2+2, then we're going to end up here, okay, with this with this chain here. So just check out how the arrows are being moved. That metal carbon double bond breaks there, and that guy breaks there. So we end up there with that guy. That guy sees another alkene, and we have another 2+2, and the whole story starts again. And so on and so forth, and you can basically continue this process ad infinitum, and you end up getting a polymer. Do you see that? So this is an example of ring opening metathesis polymerization. All right. Now, yes. All right. So that's basically the mechanism, and you can terminate it by adding some sort of a reagent. That's not so important, but you can terminate this coupling process, particularly by adding, for example, some sort of a ketone, which will then attack the catalyst, and then the chain will break off, and you can isolate it. All right, and then you end up with endo 1O. So these are the three mechanisms. All right, let's just review them. Yes?
Is it something that drives the fact that you don't get an intramolecular 2+2 again? To go back to what you started with? Because I mean...
You mean that it doesn't go back that way?
Yeah, but like not when you have, let's say the second step.
Yeah?
Yeah, like it could also go back, right? Because you have a
Yes.
bond. Is it something that drives it the other way? Or?
Yes, that's a very, very good question. In fact, another question is, why did we just get ring opening metathesis? In other words, why does this thing polymerize? I mean, if I take this alkene, it's a cyclic alkene, we also have ring opening metathesis, ROM. Why doesn't it just stop there? Well, it depends on the catalyst, it depends on the ligands on the catalyst, it depends on the concentration of the substrate, it depends on reaction conditions. So that's an important point. The mechanism is the same, but whether it goes in the direction of polymerizing, like we see here, or in the direction of ring opening, or as you say, in intramolecular process, those are things that are dictated by ligand design, right? Electronics, sterics, and so on, and concentration. For example, think about this. If I go back to the previous example, just sort of to underline this point. If I want to do, let's suppose I want to do ring closing metathesis of this guy. Now here's a question. Okay, remember, because the mechanisms are all the same. We could have competing reactions. We could have ring closing metathesis, as we see here, but we could also have cross metathesis. Because, for example, I mean, remember, I have other dienes floating in the solution. So if I'm at this intermediate here, at this intermediate here, in principle, instead of having an intramolecular ring closure like I've depicted here, what could also happen?
Another fragment.
Correct. Another substrate could come in, another one of these guys could come in, and you could basically form a cross metathesis product. Now that's the point. How would we control that? Well, it depends on the catalyst, for one. It depends on the ring strain. In this case, we end up with a 6-membered ring. It's pretty stable. If you had like a 4-membered ring, if you were trying to make, let's say, a cyclobutene, it probably wouldn't work, and you'd get cross metathesis. But what else can you do? Something very simple to prevent deterioration in the selectivity. Let's say I want to make a ring-closed product.
You could like add the substrate like slowly.
Exactly. Or at very low concentrations. Precisely. Because if you have a very high concentration of that guy, there is a chance that at least to a certain extent the selectivity is going to deteriorate because you're going to have this cross reaction taking place as well. So these are issues a person has to take into consideration when looking at these different types or variations of metathesis. And the same thing here, okay? Now let's go back to old Grubbs. This is the first generation catalyst. And well, like I said earlier, now that we've looked at the mechanism, I think now we can go back to looking at catalyst design. This is the catalyst. How many valence electrons does this guy have? What is the oxidation state? Let's assume it is Fisher time to help us. You remember how to count? I don't think we did that in the 2000 course. But how many valence electrons does this have?
7?
Is ruthenium declined? It's declined, right?
No, ruthenium is group 8.
A 6?
Don't look so concerned. Everything's going to be all right. 16 or 8? It's 16. If it's ruthenium 2, it's D6. We can't, well, you know, if it's Fisher type, that's a 2 electron donor, so it's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, one would therefore be tempted to say, okay, well, if it's a 16 electron compound, then what would be the mechanism? Well, we've looked at the mechanism a moment ago, but in those catalyst cycles, I started with an M double bond C, right? Now the question is, here's the question: is this the active catalytic species? Yes or no? In other words, does the alkene react with this guy here and then do the 2 + 2 cycloaddition and all the subsequent steps? Explain. Think about that. Well, it's 16 valence electrons. So let me maybe just write down what I mean. Is this, if we say we're using the first generation Grubbs catalyst, remember CY is tricyclohexylphosphine.
No, it has to pass one of the PCYP.
Right, but just a moment, I'm saying, is this now the starting point in our catalyst cycle? And then it goes round and round and round, yes or no?
No,
Why not?
because it's 16, so the alkene can just go in the matter. Instead of metalysis reaction, we just go in the
Well, I mean, if it's 16, it can accommodate an extra 2 electrons because of the 18 valence electron rule. So, in fact, one can argue that that's perfectly reasonable, right? That you basically have that, then you form an 18 valence electron intermediate, and then it does the chemistry. But the answer is that's not what happens. Because if it forms an 18 valence electron complex, it's going to be stable, and nothing's going to happen. Moreover, due to sterics, this is impossible. Think about it. Look at the structure there. There is the metal-carbon double bond. Do you all see that? Where on earth is an alkene supposed to coordinate there? It's impossible from a steric perspective. There you can clearly see it in the space-filling model. So what is required is that the tricyclohexylphosphine at the bottom here, check it out, needs to decoordinate from the ruthenium, which happens because, you know, it's in solution, so you have these complexation equilibria, and that we form a 14 valence electron hot reactive species, which then picks up the alkene. They're spaced at the bottom, so that's precisely what happens. You lose a phosphine, you lose this tricyclohexylphosphine in solution, and you have this hot 14 valence electron intermediate, which then sees the alkene and grabs it and you start the cycle. Or you have ring closing, ring opening, cross, whatever. That's the active species. Now here's the question. If you're a scientist, right, and you Grubbs, and you've made this guy, and you see, oh, it does Grubbs metathesis. Well, it wasn't called Grubbs metathesis. It does metathesis of this guy. That's great. It's a catalyst. Wonderful. Let's write a paper and submit it to Journal of the American Chemical Society, which is precisely what he did. Now, if you're a scientist and you want to make a better catalyst, what would you do?
Better, like a better ligand that detaches more easily.
A ligand that detaches more easily, yes, because we've just said that this tricyclohexylphosphine group needs to detach before the alkene can coordinate, and we can start this glorious process of 2 + 2 cycloaddition, cycloreversion. So a ligand that detaches more easily, good idea. What else can we do?
Do reductive elimination.
Reductive elimination of,
I don't know, something.
well, check this complex out, right? Do you see that these two tricyclohexylphosphine groups are sitting opposite each other? They're sitting trans to each other. Now, remember, they're pushing electron density both into the ruthenium, which is in the middle. And if the one pushes more electron density into the middle from the top, for argument's sake, what's it gonna mean for the ease of decoordination for the one at the bottom? Yes. So it's very simple. If we increase the sigma donor capacity of the ligand at the top, we're going to facilitate decoordination of the ligand at the bottom, and therefore we're going to achieve the formation of this 14-valence electron complex faster and potentially increase the rate of the reaction and the catalytic turnover. And that's precisely what they did. They made, this is a second generation Grubbs catalyst. All that they've basically done is taken this over here. This guy here is called an N-heterocyclic carbene. N-heterocyclic carbene. And that N-heterocyclic carbene basically is a much stronger sigma donor than a phosphine. In other words, that's pushing a lot more electron density into the ruthenium, and that's making the remaining ruthenium tricyclohexylphosphine group more labile. So this facilitates decoordination of PCY3 more readily. And that increases the rate of the reaction of the metathesis. So that is the one advantage. The other advantage is it turns out that the thing is more stable. In other words, you can handle it longer in let's say in the normal atmosphere. The tricyclohexylphosphine one was a little bit more prone to oxidation because phosphines tend to undergo oxidation to form phosphine oxide. So this guy, more stable, more active. Second generation Grubbs catalyst. Now here is basically just to show you some more data which comes from this review if you want to read a little bit more on it, investigating the kinetics associated with the decoordination of the tricyclohexylphosphine for the first and the second generation Grubbs catalyst. This over here, H2IMS, is just a representation of this ligand here, this N-heterocyclic carbene. Now an N-heterocyclic carbene is a ligand which is isoelectronic to a phosphine and has 2 electrons sitting in a carbon atom which donate strongly to the ruthenium. They're strong sigma donor ligands. So basically what these guys did, this has now been studied, is the rate of, let's have a look at this, basically of coordination and decoordination. So this is K1, K minus 1, right? And then the second step, of course, as I've said there, would then be coordination of the alkene to the 14-valence electron reactive complex. And we call that K2, K minus 2. These are equilibrium processes, obviously. Back and forth, back and forth. Now, what I'd like to say at this time is just look at these numbers. What do these numbers tell us? For tricyclohexylphosphine, it's 10 to the minus 4. K1 is much faster, but K2, relatively speaking, the ratio of K2 as over K1, K minus 1, is much lower. It's 4 orders of magnitude lower than in the case of the N-heterocyclic carbene, which tells us that from a, let's say, kinetic point of view, the second generation catalyst is going to do things much faster, which is what you can clearly see here, reflected by these values. So that is basically proof that the N-heterocyclic carbene is much better, hence the second generation catalyst. There is also another catalyst, we call this the Hoveda-Grubbs catalyst. Now this is something that Nicole said earlier. We've got two things we can change. We can change like we did in the second generation Grubbs catalyst. We can replace the phosphine with the with the N-heterocyclic carbene, increases the sigma donor strength, facilitates decoordination. What we can also do is play around with the thing that is coordinated at the bottom here, right? So what we did by decorating it with replacing the phosphine with an N-heterocyclic carbene is increase the sigma donor strength and therefore increase the, as we saw now with this kinetic data, the lability of that phosphine. But we can also change the ligand here. Now what they do in the Hoveda-Grubbs catalyst is instead of having another tricyclohexyl phosphine ligand at the bottom, we have something like this, right? And this is essentially an ether group that is coordinating to the ruthenium. That is a neutral oxygen atom with lone pairs. It's like an ether, well it is, it's an ether, isn't it? An ether functionality bound to the phenyl ring, and that's coordinating to the ruthenium center. Now, ether coordinations or oxygen coordinations to transition metals is very weak, except if they're early transition metals. For example, if you have complexes of yttrium, scandium, lanthanum, you know, these very early transition metals, they're very oxophilic, and you often see that they love oxygen. And if you have an ether functionality, or THF for example, diethyl ether THF, it sticks onto those metals and it's very difficult to get rid of it. But ruthenium is not an early transition metal, it's not so oxophilic. So this coordination here, this ether coordination is going to be extremely weak, very weak. And so what this basically is it's kind of like it's a source of this hot 14 valency electron active catalyst species there, sort of in disguise. Because the moment this guy goes into solution, that O is